So for those of you who don't know me, my name is Daniel Wigdor. I'm a professor here in the DGP lab. Thank you for joining us in the lab. And as you know, our talks are divided between Sanders Series invited lectures, where the lecturers travel from all over the world to come and give our talks. And of course, we alternate with member presentations. And I'm very pleased that for the very first time, we are including a student as one of the member presentations. It's the very first one in the 4-year history of Tux. And I'm very pleased that it's Haijun who is breaking that glass ceiling. So Haijun is a PhD student here in the DGP lab. And he has been working on his PhD here for several years. He finished his master's degree here before that. And before coming to U of T, he was an undergraduate student at Tsinghua University in Beijing. Over the course of his academic work, he also has worked for several commercial enterprises on internships and through other relationships. He has worked at Microsoft Research, at Autodesk Research, and has also studied under Ken Perlin at NYU on an internship and under Manish Agrawala at Stanford. And both Ken and Manish have been Sanders Series invited lecturers here in Toronto. Haijun is quite a character. And so, this is my opportunity to sort of, say whatever I want about him, right? What drives me absolutely crazy about him is that he doesn't publish a paper that doesn't win a Best Paper Award or a Best Paper Honorable Mention. And I'm not sure how he's gotten the fix-in on the committee, but he definitely has figured this out. So over the time of his studies here at U of T, he's published 8 full papers at WIST and at CHI, and a whole 4 of those have been awarded Best Paper or Best Paper Honorable Mention. And I think what's really exciting about Haijun's work is that since the advent of the fundamental mechanics of interaction in the 1960s, and then the user interfaces that sit on top to invoke those interactions, really in Smalltalk, 1970s, 1980s, there hasn't been a fundamental rethink of the basic components holistically of a user interface. I mean, I'm sitting here using an iPad that people say is a revolution in human-computer interaction, but it's still just a bunch of buttons and sliders and scrolling lists and things, right? But what Haijun is able to do is to approach user interfaces as a science and apply a deep understanding of basic human capabilities and needs, and to build fundamentally new interfaces that target the domains appropriately and to build these fundamentally new user interfaces. So I'm very excited that Haijun is going to come and speak with us today, and he'll be on for the first half hour and then we'll pass along. Welcome, Haijun.
Thank you for the introduction, and I'm very honored to be here to condense 5 years of my life into 30 minutes. So, from the dawn of computing, generations of HCI researchers have been trying to use computers to support creativity and productivity. And when I made the decision of doing a PhD, I want to do the same thing. So I came from China and started working with Daniel. So when I first met Daniel in his office, he said to me, "I want you to have this." So this is a Moleskine, and I'm actually not sure whether this is the original one, because over the years I have collected so many of them. And at that moment, I thought he just wanted to give me a notebook so that I can take notes in the meetings. But actually, that very moment defines my PhD research, which is to figure out why Moleskine is a better tool to support our creativity than a computer. And I assume many of you have computer science background, and you might share the same obsession as me, where I'm so excited of all the new computers and machines coming out every month. But let's face it, when we want to be creative, we won't go to the computers, right? We push away the keyboard, we close the lid of laptop, we get a sketchbook and some pencils, or we go to a whiteboard to start sketching. And why is this, right? So let's take a look at how we use drawings or use Sketch to assist our thinking and creativity exploration. So imagine you're with this group of people, and you said to them, "Look, guys, we're out of food for the winter, and we really should hunt this thing down." Then you go to a whiteboard and you draw this. And you say, "Obviously, we can get enough meat. We can also use the skin to stay warm in the winter. And we can also put a tusk in front of the gate to protect us from the animals and other tribes." But then one person stepped out. How are we going to hunt this thing down? And then you go to another whiteboard And you say, we can have 3 archers to hunt on the big one, and use one to scare away the other smaller one. The other person disagreed, and he drew this. He said, wait guys, hunting the big one is too risky. Why don't we put our best archers on the smaller one and just use 2 to scare the big one? But this one person didn't agree. Well, he said, well, I agree, but there's one thing we need to make sure. These things runs really fast, and we need to figure out a way of shooting them. And he goes to the whiteboard and figure out the math of what's the perfect shooting angle. So what are we seeing here? We're seeing that these people use really primitive technologies like rocks and walls to figure out really complex tasks. And the magic here is the drawings, right? Which offload and represent our complex mental process into the thing on the wall, which we can use to communicate with us, with other people, and to figure out this task collectively. Now, today, when we say we want to support creativity and reasoning, we're mostly talking about user interfaces like this. And let's walk through another example of how to use this interface to achieve very simple design. So here I got this design, and I want to make some changes of the color. So I want to change the color of these 2 objects because they are too bright. I want to tune them down. I want to reuse the color that I have over there. And because I know this is Illustrator, I know there's this eyedropper tool which I can use to copy all the attributes. So I go to that eyedropper tool, copy that object, and that's not what I want, right? The eyedropper copies everything. All I want is just the fill color. So it gets rid of the stroke that I already spent a lot of effort on. So all I can do is to undo that eyedropper operation, go find a different tool, which is a selection tool, select the object that I want to share attributes, open its color palette, select that text that represents the color, copy it, reselect those 2 objects, open that panel again, reselect this text, and paste that text. And hit Enter key to confirm the change. And imagine you want to try different colors of all the other objects. You have to do all these steps. So what's happening here? Well, what do I want to communicate with the computer? I want to tell the computer that I want to use a color of X on Y, right? But I have to do all these operations on the interface to achieve that one simple task. And I think the fundamental problem is that the computer and us do not speak the same language, right? Every simple intention I have, regardless how simple it is, we have to translate it to a sequence of operations that the computer understands. And if this is the interface you use, every operation you do is like this, it's kind of boring, right? It's really frustrating and time consuming. You're not doing design, you're literally you're working with a machine like a machine to achieve what you want. So the core of my PhD work is trying to enable the users to directly and flexibly express their intent to the computers and effectively integrating computation into our thinking process. And I approach this through the development of human-centered interaction language. And I would argue that to achieve better interaction with the computer, we need to put aside the interaction first and to figure out what actually affords the interaction, right? So in this example, what affords the interaction, or what's the thing that I spend a lot of effort on? It's this piece of text, right? And what can I do about it? I can select it, of course. I can edit it. I can cut it, copy it, paste it. I can also search the text with Google or do a spelling and grammar check on the text. Clearly has nothing to do with what I want, right? So the problem is that different from the drawings on the cave wall, which represents our mental processes as we want, this is a really rigid representation and it doesn't work with our mental process. So everything I do, I need to translate into these operations. And I think we need a different representation on the interface. We need a representation that directly reflects our intention and also provides suitable interactions so that we can articulate that intention to the computer through the interactions. So I have worked on so many of these projects which have the same vision. They looked at different domains like data illustration, vector graphics, 3D editing in VR, and brainstorming activities with different devices like a tablet, a Surface Studio, or a large surface wall, or in VR. But today I'm only going to focus on these 2 works. And I'm equally proud of all the other works, and I encourage you to check them out on my website. So if in our mind, what we really care about is an attribute, where when we're thinking attributes, we want to say, I want to reuse the attribute on one object, right? I'm thinking of it as an object. So if we're referring to as an entity in our mind, why don't we make it an object on the canvas directly? So with this interface, if you tap on the object, you see the attributes of this object. They are not text, they are just this card, which you can tap to see the sub-attributes. What if you want to get rid of an attribute? You just remove the attribute by dragging it out from that object, or you push it back to add that attribute back to the object. Or you can add new attributes by opening up the sort of a menu or whatever there, and you add a new attribute there. So now with the attributes properly represented as objects, let's take a look at how we share a color, right? So here I have light bulb and I have a reflection. I want the reflection to use the same color as the light, right? I want to use the color of the light on the reflection. So I tap on the light bulb, select that fill color, and tap the object I want to share it to. That's how I share the color. So if we take a look at the operations that I do, first I select the object, right? The light bulb, and select its color attribute, and reuse that color attribute on the other object with one action. So note here that not only the attribute objects significantly reduce the number of steps, but each of this step directly refers to the mental entities and actions that we have. So here, because it is represented as object, I can easily articulate and directly tell the computer that what I want to do. And there are many other things we can do with the attribute. So you might notice that when you actually share a color, there is a link icon showed up underneath, which means if you tap the link icon, you can actually link the two attributes together so that whenever you change the color of the light, you are changing the color of the reflection as well. You can also make changes of the attributes. So here, I want to change the stroke width of this object, and I can hold one finger on the attribute, which is stroke, to tell the system that this is the attribute I want to change, and slide my finger on the canvas. So here, I can also hold on the drop shadow and directly manipulate the position of the shadow. Imagine you do this in current user interface where you have this two attribute, which is offset X and offset Y, and you're just clicking that triangle button to improve or increase or decrease that value. So there are many other things you can do. You can also reuse attributes from objects on the canvas. So here I want to draw leaves with the color of the trunk, and I can just copy out that fill color and draw with that. And actually any other object on this canvas is reusable, right? I can hold on that object and start to duplicate it. We can also blend attributes. Just bear with me for a moment. There are so many things you can do if you don't do spelling and grammar check. So here, if you hold the two attributes at the same time, you can generate an interpolation between them. And you can drag this along the axis to interpolate the values. And while you're dragging along, you can use this value to color all the waves. So similar to, like when we are referring to the attribute as an object, we think of them literally no different from the object we have in the real world, where each of them has a history of their own. So this notebook is 5 years old, and my phone is 1 year old. So why don't we make each attribute has their own history? So here I made a bunch of changes of the fill color, and then I switched to the stroke and figure out the stroke. But then I realized one of the previous fill color worked best with the stroke. I can open the history of the fill color and go back to just the history of this fill color and select the previous version of it. Imagine you want to do this with all the computer software you have now, where you use undo to achieve that, right? You undo to the step that you want for the color, but with the cost of losing all the operations come behind it, right? The operations on the stroke and the operations on other things. So what this does is this distribute all the global actions you have in the computer into the smallest unit of interface, which is attribute. Of course, we have seen here that the attributes are components of drawing objects. They can be components of other things. For example, in this one, it can be a component of a layer. And I can add an attribute to the layer, and then I can adjust the opacity of this layer, and I can start to add a new layer and start to trace the tiger. Or I can start to change the attributes of canvas directly, where I can directly change the color of the canvas by changing the fill color of the canvas. Or I can customize the shape of the canvas which is, like right now, if you want to do this in Illustrator, I don't know how to do it. Like you have this rectangle, and if you want to change the color of it, you probably have to cover it with another rectangle, which is, and then you change the fill color of that. So these are the operations you can do when you stop thinking attributes as numbers. When you start to think attributes as objects, where you can directly tell the system what you want to do with the attribute. So here, so we have this formula, right? It's representation need to represent our intention, but also affords the right interaction. Let's try to use this formula to design another application. Let's say we want to build a whiteboard, as we just talked in the beginning. So when we have the physical whiteboard, we go up there, we write down, they are represented in the physical world as bits or atoms or molecules, where we can erase things bit by bit, right? But many computer applications, they state on the representation of a stroke, where you can erase them by stroke, which is very good. You don't need to do all the erase things. But there are other things we can do. We can recognize them so that they look neat and tidy on the canvas, or we can make them interactive, right? So the first task then for us is, which representation should we choose? Right? Well, as a user, I don't want to get stuck on any of these levels, right? I want to be able to work on all these levels. And so in a realistic workflow, the same concept in our mind, a list, can have different representations, right? And I think the interface should provide a way for us to go through the different representations to leverage the best functionality that representation affords. So with ReLarge, we explore the flexible representational axes, which allows us to change the representation in real time. So we have three representational axes: semantic axis, temporal, and structural. So how do you access those axes? So here I got a drawing, and you can slide your finger along the one axis up to recognize it, and swipe along the other direction to unrecognize it. So that's the only action you need to do: up to recognize it, down to unrecognize it. And let's say I want to use this whiteboard to do some planning of the budget, right? So I draw down a table. By default, this representation is a stroke, right? Every stroke is one object I can erase by just one erase operation. And I want to recognize them as a table. Now, here, the strokes defines the columns and rows of this table. But because it's recognized, and I think this two column is too wide, I want to divide them. And I can just divide them by just drawing a stroke here. Then the next thing I want to do is I want to merge all the cells on the top row. Well, I don't know how to get to the merge all cells here in this interface. And I don't know what's the gesture of it. So what I'm thinking of is, let's go back to the original representation, which is point, and get rid of all the points that I don't need, right? And then re-recognize them, push them one level up as a stroke, and then one level up as a table. And I don't think it's playing. I have a theory of why, but I will tell you guys later. So one level up to represent them as stroke, and then one level up as a table. So here, I'm not saying this is the only way you should do it. I'm saying this is just one of the ways of doing it, right? You can always go back to the stroke level and replace the stroke with shorter ones. Or if you figure out a command where you merge all the cells, you can stay on this representation, right? There is no best way of doing this, right? The best way is to support the user to do what he thinks when he wants to do that. And we should not just provide this one rigid representation of the interface. So the semantic access can also be applied to other content. Here we got a holy cow, and we can actually draw on the cow, and the stroke actually stays on it. That's a natural behavior, right? But I can also go to the pixel level, and I can start to use my finger to smear the pixels together with this person, or use my pen to crop this cow. Here, it is also interesting just to imagine in the future we can, well, maybe right now, to push this image one level up beyond the picture level along the semantic axis, where we will have powerful machine learning and deep learning algorithm kicking in and recognize the cow and the man, and they start to interact with each other. But that will be the next project. So there's also structure axis, right? So I got all these images on the canvas. I want to manage them, organize them, right? So I can first move them along structure axis to group them, and then one level up to put them into grid. And here I can reorganize them in the grid. And when I don't need to, I can swipe along the opposite direction to return to the messy layout that so that I can maybe brainstorm in a more free-form way. Of course, you may say, what if I don't want the grid layout? What if I want other layouts? We didn't address this problem here, but you can imagine we can provide these options to the users so that they can choose which representation they want to stay on. But we always want to provide this flexibility to go up and down the representations. There are also implicit structures that we can embed, which is here, like I want to create some like reading menu. So I start to trace this image, and naturally it sticks in, right? But I don't want to show this image to the people that I want to present to. I just want to show him my strokes. And I can go along the structure axis to separate them. Now I got the strokes, rather than figure out other ways of doing this. And we can also have like intermingled movement along the different axes. So here we have the most advanced list, but then we can go back to its original form. Now put them into circles, and they stop being a list, right? Because now there are nodes that in my mind, and I can recognize them as nodes and diagram, and start to sort of make a node diagram. Here I recognize them along the structure axis to group them, and then separate them into different layout, and then I can sort of start to connect with them. Wow, I do draw really slow in this design. And there are also temporal axes we can play with, right? So when you have one final design, you want to show other people, sometimes you want to show the progress to this stage, right? So the temporal axis allows you to go back to the previous versions of this representation. So here I make a copy of the current version, and I can go back to history, make a copy of this version, and try to do this many steps just to highlight the key steps in this design. And okay, this is the original version, right? And then I can go to a different slide and pull out all these different designs so that the other person can see this sort of like incremental changes of all these designs. And there are many other things you can do with the representational axes. Sometimes as a HCI researcher, we need to figure out how many user studies we need to run. So we go to whiteboard, we write down all the conditions. And of course, right now, if I want to calculate how many trials, I probably have to pull out my iPhone. But here, with this, I can recognize them and make them interactive so that I can start to play with the numbers on the board. So here, I want to leave you with this project where there are many things we can do with this. But the key thing here is that one representation is not enough, right? There are many representations of the same concept. And the interaction should really adapt to what you need and really achieve what you want at that moment. So I want to leave you with this sort of final thought. And I think representation matters. They shape ourselves and they afford interactions. And a good representation should always directly reflect and dynamically adapt to our mental model, and always afford suitable interactions based on the context through which we can articulate our intention and communicate with the computer. And if your computer is not speaking the language that you speak, maybe this is where it deserves. And with this, I want to thank you for your attention, and I think everybody should get their own skin. Thanks.
A minute for questions, if anyone has any.
Yep.
Thanks for the great talk. I didn't know much of the details of your project, so I enjoyed it a lot. I have a probably naive question about the table. What if you want a mix of flexbox and recognition? How do you handle this? We didn't talk about that.
That's really tricky. So right, that's sort of our design right now is, well, there are different modes of design where right now we see the context, right? The context is the table, and then we recognize the drawing. But you can always say, don't use that context. That's another more direct, maybe more free-form way where you recognize the table, and then whatever you write down is still in the analog form. But then the question is, how do we get to the same level? So here, you're sort of essentially you have different levels, and now if you maybe push them up, you always push the lower level up, and then then moving them together. But that's but you also maybe want push this level up, and then keep this one at this. So I think there is a lot of things to explore there. That's the next project. Yep.
Did you find any limitations to the first, the drawing interface in terms of number of options? And then you did show the example with the layer, but is it sort of optimized for parametric type tools? Did you find any other, and did you find any limitations or new ways to sort of work with that kind of parametric model?
So that's exactly
That
where-
Adobe doesn't, like, wasn't built on that, like Illustrator wasn't necessarily built on that, but they've sort of added those features. Is there anything you discovered in that interface of where that could be improved or thought, like,
That's where, like, that's actually why we start with attribute, because we recognize that, you know, in a lot of design, a lot of software use, like 3D modeling, all you are doing is actually changing the parameters, right? And the current user interface just show you the parameters and lets you just change the parameters. But we want to incorporate it with another layer which matches our intention better. Of course, like, this is really for this kind of design. But if you say, I just want freeform drawing, I just want brushes, you know, that's a different realm, right? Like, you know, artists may say, I actually don't want to use the parameters. I just want to play with different brushes, right? Where I have brushes with different sizes, with different colors. But then again, your tools have attributes. So, you know, the attributes can be applied to those as well. But in our exploration, we're only focusing on the parameters of the content, but not on the tools. So a lot of designs, the tool is a good representation, a good abstraction of a bunch of things you do. So like if you have one tool you draw, and there are many parameters you are adjusting simultaneously, right? So this is not touching that part, but it's, because tool is already a good representation. Yep.
I noticed you've relied a lot on two-handed gestures in that UI demo.
Right.
Did you explore one-handed things? Because, you know, the Moleskine is great because you only need a pencil and one hand. So do you explore analogs for one-handed versions?
So we want to show what you can do best with by manual interaction. But like if you look at the most complex gesture I use in this interface, which is just pinch, right? Like you can use pinch to sort of like to do all the just one hand pinch to do the operations. But at some point, like where many scenarios where we hold it with one hand to set the mode, to tell the computer that this is temporarily that I want to be, like I want to reuse this color, and then I draw with my pen. That's where, you know, things get conflicted. And I think one thing you can do is maybe just tap it and sort of pin this mode. But the downside of it is you're changing it from that sort of like temporary mode where you hold with your own finger and muscle to a permanent mode where you're pinning on the interface. And, you know, like you might forgot it, and like you say, I want to use the original color, that you actually are stuck in the mode. So I think that's a way of working around, but it has some downsides. Yeah.
Okay, thank you, Haijun. Two for the price of one admission today. So I'm very pleased to introduce Seongkook Hyo. Dr. Hyo is a postdoctoral fellow here at the DGP lab at U of T, and he joined the DGP about a year and a half ago. And in that time, he has, although he already was a great collaborator while he was doing his PhD work at KAIST, he has very quickly come to be sort of a junior faculty member here in the lab and really had a lot of impact on a lot of student projects. So the fact that he only has half an hour here to show the breadth of his work in this time is really unfair. But before Seongkook joined U of T, as I mentioned, he completed his PhD at KAIST. In addition to that academic experience, he also has worked at several research labs on internship, among them Microsoft Research and Autodesk Research, and also Samsung. In his time as a researcher, he has, I think this is sort of interesting, completed 19 peer-reviewed publications in conference venues and filed 23 patents. So his portfolio of intellectual property is quite extensive. I think what's really exciting to me about Seongkook's work all up is that although when you say haptics, right, and people immediately say, oh, you mean force feedback. It's almost like the two concepts are synonymous. And immediately this evokes, in people my age at least, the little rumble packs that came with the Nintendo 64, or these other sort of like anemic little vibrations that you experience. And I think what's really exciting to me about Seongkook's work is, first of all, he teaches us that force feedback and haptics don't mean the same thing. And he does that by exploring an area that has been largely unexplored in the area of haptics. to try to enable us to interact with computers in fundamentally new ways. So I'm very excited to introduce Seongkook, who will tell you now about his work here.
Thank you so much for the introduction. Before start, let me first show you a video of myself playing the guitar. I'm not a great performer, but here you should be able to hear some sound. So yeah, you should be able to hear the changes in the sound by myself changing the slightly changing the pulse movement or which part of the hand or finger I'm trying to use to stroke and make the sound. So I make variety of changes here, and I also can play the guitar with my eyes closed because I can feel the strings and I can know where my hands are, where my fingers are, where the frets and all the things of the guitars are. But here's another video of myself trying to play the guitar on my very expensive iPad and without seeing it. So I'm trying to feel the music without like seeing the iPad screen and trying to play the same music. But I can't even make a single chord sound right? And even if I can do, I can't control the subtle nuance of the sound like I did with the real guitar. I can't make subtle differences in the like pitch or the like way it sounds. And I think this limitation comes from the limited interaction bandwidth between the humans and computers. When we interact with the real-world objects like this guitar, we fluently control the movement and the forces and the physical like aspects of our interaction. And also the physical objects we interact with, they are affected by all of these parameters and values, all the physics. And also, we feel the status and the changes of the physical objects from our touch, right? That is what makes the physical interaction very easy to do and very rich and nuanced. But for computers, even if we make a very physically complex gesture, the computer only sees it as a movement of a cursor. And we can only understand the virtual world through a visual channel. So we see the icons, we see the visual feedback. We can't actually have the holistic experience we have in the physical world. And I think this is really problematic because it is not that we're bad or the computers are bad. Both humans and computers are extremely capable of doing much complex things. Today's computers, even mobile phones, could create really high fidelity sound or have really rich, compelling virtual world in it. But all the rich experiences that are possible in this computer, or all the rich manipulations we can do with our body in the physical world, they're kind of blocked by the computer interface that kind of diminishes our experience, and it is wasting all the capabilities we can do with these great computers and our great capabilities. So my vision is to expand the interaction bandwidth between the humans and computers by developing new sensing technologies and haptic feedback technologies, and also the interaction techniques that defines the language between the humans and computers. So today I want to share some of the research projects my colleagues and I have done to expand the interaction bandwidth and what we can do with it. So I'll start from expanding the information flow from humans to computers. And here's how we did. So we used the information obtained from the physical collision between us and the computer. So, and we can also utilize our capability of knowing and controlling our body movements and utilizing the computer's ability to infer context. So we want to have all these available for computer-human interaction. And I want to explain one by one from the contact mechanics. So when we make a contact, many things happen. And let's look it closer. And here you see the finger. And when it touches, not only the position changes, but there is also some force exerted on the surface. And in the real world, we use that force to differentiate our manual interaction. And this is a cap of a medical pill bottle. And to open the cap, you have to put it down and rotate. Otherwise, it will just keep rotating and nothing happens. And this creates two modes in the real world, opening and free rotating, and it will prevent your keys to eat these cute little candies in a fancy bottle. And we can have such modes on touch screens as well. So if a touch gesture is made without any force, the gesture will be registered only within an application. But if some force is exerted, the mode changes, and the gestures are registered to a higher level application manager. So, and this is a demo video of a force-enriched interaction technique on modified iPad Touch device that can sense force. And if you drag a picture, it will move in the air, right? And if you exert some force without lifting your finger, you can still have your picture under your finger. And you can switch between different apps. So by doing this way, you can drag and drop the picture between applications without having to deal with those long press and selecting different buttons, so that we can have a more efficient and easier way of dealing with contents by using these different force-augmented modes. And let's look closer to the touch. Here, if we look closer to our touch, there is a contact between the finger and the surface. And this contact area becomes larger if we press harder. And the amount of contact area increase for the same amount of force changes by the softness of our fingertip. So if our hands are or fingers are harder, the less contact area change is happening. And this softness changes is really important in the real world. It changes nuance in our interaction. And think about a scenario where you're playing percussive musical instrument, like this bongo. And we use different hand parts with different softness to create different sounds, right? And we developed a method of measuring the hardness of the hand touching the surface based on the changes in the contact area and the force. And using that information, we can make an application to react differently by how soft or hard the touching finger is. And in this painting application, you can scratch the paint by using the hard fingertip or smudge the paint using the palm area. And also, you can play the drum sound differently by the hardness of the object touching the surface. Yep. Maybe if someone more experienced in that instrument, probably the sound kind of better. But yeah, we could see that utilizing these mechanical parameters involved in the touch could greatly make the touch interface to be more efficient and more expressive. But our body or the physics is not everything. We have the proprioception. We have the ability to know where our hands are, where our muscles are, and how we have to plan to make the movement we want to have. And we want to use this proprioception, and before going into detail, I want you to try this. So make your fist with your left hand and try to tap this part of your wrist using your right index finger. And now tap this part, your hand. And again, the wrist and the hand. And now don't look at your hands. You're already not looking at your hands. And try doing that quickly. Yeah, wrist, hand, wrist, hand. Is it difficult? It is not difficult at all, even if you're not seeing it, right? So we know where our fingers are and where they're going to. And because of that, we can do this complex gesture. Maybe if you're using a mouse and you have this picture on your display, if you're trying to click those two parts without seeing it, it's going to be really difficult. But we have this skill which is not being utilized on touch interfaces. And I wanted to know if it is not really being used on touch interfaces. So we conducted this data collection study. We collected touch events when people were using tablet applications. like email applications, social media, or browsing the web, or writing a document on an iPad. We collected over 14,000 touch events. And among these touch events, we extracted tap gestures and projected the time and distance between the tap gestures on this graph. So the horizontal axis is the time difference between two tap gestures, and the vertical axis shows the physical distance between those two tap gestures. And if we look closer to the data, we can see those tap gestures are not really related. So yeah, they're just separated tap gestures. They're just too far from previous touch, or they're just too they just made after 500 milliseconds or more from the previous tap. And there are double taps, when people made two taps at a very close distance within 500 milliseconds of time. But you can see this large area with no tap gesture found in it, which is the distant tap gestures that are made within 5 milliseconds. We call this gesture consecutive distant taps that we just did with our fingers. And using these consecutive distance taps, we can do scaling or rotating all those multi-touch gestures with a single hand without having to use your left hand. Or we can call a pie menu without having to find different UI buttons. We can have different free gestures that were not available or being used in previous touchscreen interfaces. So we found that our ability to understand where our fingers are and where our hand positions are, and quickly controlling it, could broaden the interaction bandwidth. And these are great, but let's think about the computers. So we've been doing a lot of things, but computers are not doing anything, right? So computers are not like static object, like a piece of plastic. It is dynamic. It can probably think, and it can react to people, right? Like when we have our dog, when we move our hand to the dog, it will come close to your hand so that you can easily pet, or they will probably bite if you're hungry. But what if we can make computers to do that? Computers can infer context. They can know what's going on based on their information. So if the computers have more information about our touch, can infer the context of our intention and respond appropriately to it. And we have this phone that can detect the hand and the finger around and above the device, even if it is not touching the surface. And by using that information, we can make the phone to be more responsive. So here, I'm watching this snowball jump video, and there is no visual clutter, no visual buttons, GUI buttons, and I can just watch the video, but I want to control the video a little bit, and I want to move my thumb a little bit so that I can control it. And the phone knows that it is being held with right hand. And it also knows that my thumb is approaching to the screen. So it can display user interface controls that are easy to be controlled by a thumb of the holding hand on the right side so that you can easily reach and control. Of course, if you're using your left hand, it will display the controls on the left side soon.
Hey, restart. I have a theory, I'll tell you.
Okay. Oh, right. Here you go. You have controls on your left side, and if you have both of your hands available, it will display more advanced controls so that you can have more freedom. And in addition to showing interfaces in a more appropriate way by the user's context, the computer can also infer the user's intention of touch based on what happened before the touch was made. So look at this Twitter application. The tweet is a button, and there are different small buttons that are used to retweet or like a tweet. But they're so close to each other, they're even overlapping. And it is so easy to make mistakes and accidentally like some weird tweet and people asking you or just trying to avoid you. And yeah, this is what's happening right now. But we make different movements when selecting targets in different sizes. And this graph shows distance of a finger above the screen, which is on the vertical axis, and the time, time on the horizontal axis. And when you're selecting a large target, you move confidently. You just quickly approach to the target, you quickly tap the surface, and this is this green line shows the trajectory when you're selecting a large target. But if you're trying to make a small target selection, then you make a subtle adjustment before actually making contact so you won't make a mistake. So by using this information, the phone can understand what the user's intended target was. So when processing the touch event, it can select different targets before the user notices it. So when the user touches the small target very confidently, it will just open the tweet. And if it was carefully made, then it will select the target that's small. So these contextual inference of a phone can allow us to have a more accessible, more expressive, and better interfaces. And those set of interactions can make our interaction better, so that we can have more efficient and expressive and efficient, more accessible interactions. But like I said earlier, the information flow should be bidirectional, so that we can better understand the context of the virtual world without seeing it. So when we feel the physical world, there can be two types of feedbacks. First, when you're initiating the interaction. So when you're touching something, you can feel the shape. When you're pushing something, or like when you're poking the steak that you're cooking, you can feel the reaction forces, and you can tell how much it is cooked. Or you can rotate the volume knob when you're driving a car, and you can tell it is rotating, and when it reaches the limit, then you can say, oh, it is turned off. And another is the active feedback, where other object initiates the touch. So when you're holding a kid's hand, and if he wants to go to the right, he will pull your hands to the right, and you can feel it, right? Forces coming from the outside. And I wanted to have all these feedbacks available for computers. And I will go first for the reactive feedback. And when you want to have those reaction forces or reaction movement, the easiest way and more straightforward way would be having to have a robotic structure that will move the surface. But having this structure makes the device big and bulky and heavy, which makes it more difficult to be carried around. So instead of using the real movement, we wanted to have a more simple and lightweight device that can be carried around all the time. And we wanted to have, we developed a haptic feedback method and use an illusion of the movement. So not real movement, but just let you to feel that there is a movement. And this is our haptic illusion model. And an object is placed on a textured surface, and it is stringed to 4 walls using springs. And this is a simplified view for better animation. And if you apply force to the object towards northwest direction, it will move, right? So it will move, and while it is moving, it will create some vibrations. Because when an object is moving on the textured surface, it creates some vibration and sound because of the friction between those two objects. And by simulating such friction-induced vibrations, we thought we can make an illusion of a movement, even if the object is not actually moving. And this is a device we built to test this method. And this device has a rigid surface, so it isn't moving at all. But it can sense the tangential force applied to the surface, and it has a vibrotactile actuator that can create some vibration on the device. And you see the black dot there, that is the position of the object. in the computer. So if you apply some force there, it will move, and you hear some sound, right? So as the virtual object moves, the computer is creating some friction-induced vibration, and you feel like the object you're pushing is actually moving around if you're not seeing your hand. And we had a user test, and all our participants said that they believed that the surface was actually moving. And because the haptic movement is controlled by the software, we can programmatically control its stiffness and its movement distance and all the physical parameters like the surface roughness dynamically by the computer program. And also, you can have constrained movement. Like in this case, you can't move to the left. You can also move to the right, like you have a physical obstacle on the left side. And this kind of interface can give you some feeling of movement. And it can be useful for force selection tasks, like if you're trying to use the force interface, and if it is not moving, users feel frustration and fatigue. But by using this technique, people felt less fatigue and less frustration. But also, if you have this kind of virtual movement enabled in your car, assume that you have this virtual joystick on your steering wheel. And if your navigation is sharing that information with the joystick's movement can be constrained, and it will guide you to feel the path you have to take. So you don't need to see the navigation screen to know the path, and you can feel from your hand. And this method could create the reactive feedback and give some more contextual information about the touch or the virtual object, but it cannot simulate external forces, and it's the limitation. And it is about our feeling of weight or forces, and this kind of sensation is very important to make you've experienced a virtual contact to be realistic. And this is a very famous problem in VR. And because it is very important, there has been a lot of different research projects and different devices to create force feedback by pulling or pushing the environment. But because of that, those devices have to be installed in the environment so that they can't be easily moved, and you have to stick to the task to use that. And instead of pushing or pulling the fixed environment, we developed a new device named Thor's hammer. We wanted to have it push or pull the air that's everywhere we can live. So it makes some sound, but it creates some feedback. So this device has 6 motors and propellers, and those propellers create some force in 3-dimensional axis. And it can create forces up to 4 newtons, which is similar to the weight of a 400-gram object felt in your hands. And by using this device, we can feel the flow of the water in the virtual world. You can also feel the buoyancy force that is upward, so that you can feel the water flow without seeing it. You can actually experience that. And also we can feel the tugging force if you're walking a leashed lamb in the virtual world. So you can chat with others while walking the lamb, and you can tell if it wants to go to the right. And you can also feel the change of the weight. Assume that you have a hammer in your hand, which you have, and you travel through different planets with different gravitational forces. The weight of the hammer should be felt differently. And we can also feel the reaction forces of the virtual buttons. So you can tell which one is a stiff one, which one is broken, which one is softer. So these feedback methods could make us to better understand the content and the context of the virtual world. And with all these projects we have done, my awesome colleagues and I have worked on these projects, and we wanted to expand the interaction channel between the humans and computers. And I think we could find how our manual interaction with computers could be enriched by using those physical objects or physical values or previously wasted precious information. And we started from the use of our hands. And I think it was quite successful, but our interaction in the real world are not just hands. It is much more holistic. So look at this video. When our hands are busy, we use our foot, right? It is. I'm not playing. Okay. We use our foot, right? And when our hands are dirty, we can use different part of our hand, right? So our interaction in the real world is really holistic. It is not just hands. Sometimes it happens on other body parts. Sometimes it happens in combination of different body parts. And I wish our interaction with computers could be like that. I wish the computer can understand how we interact, how we want to touch, how we want to experience the virtual content. And I want the interaction techniques to fully utilize our capabilities of planning, rooming, and filling the virtual world. And so that we can fully utilize the rich capabilities and power of the human and computers. And that's the end of my talk. Thank you so much for your attention.
We have time for 2 questions. Food plus heat. None at all? All right, well, we can wrap it up there. Thank you, everyone.